Hi, in the last few classes, we were discussing about orthogonal curvilinear coordinate system. We obtained the general expression for the divergence, the gradient, the curl uh, of the expressions for finding these quantities, the gradient, divergence and curl in the orthogonal curvilinear coordinate system. Now we apply this to a particular curvilinear coordinate system, the circular cylinder coordinates. Circular cylinder coordinates. So here we have three variables instead of q1, q2, q3. We are using rho, phi and z. So these are the three variables, q1, q2, q3 and rho, phi, z. Okay, and the rho is the perpendicular distance to the point from the z-axis. So this is rho. Perpendicular distance, this angle is 90 degree, and phi is the angle around from the x-axis to the projection. Okay, so angle around from the x-axis, and z is same as the z of the Cartesian coordinate system. So these are the three variables we use here. Okay, so what are the surfaces? Rho, as I said earlier, is a perpendicular distance from the z-axis, and phi is the angle around from the x-axis, and z is z. Okay, so the three surfaces are, first one, rho constant. Okay, rho constant. What is it? Right circular cylinders having z-axis as a common axis. Right circular cylinders having the z-axis as a common axis. Okay, the rho constant that we can see here, this surface. Okay, this surface. Everywhere on this surface. Okay, everywhere on this surface, rho is a constant. Rho is constant. Okay, now the rho constant surface, that is a curved surface. Then the second surface, phi constant, that is half planes through the z-axis, phi constant. Okay, the half planes through the z-axis. So it is this. So this is the z constant, phi constant surface. Then the z constant surface, that is planes parallel to the xy plane. Okay, as in the Cartesian coordinate system. So here rho constant, that is a curved surface. Okay, rho constant, that is a curved one. Okay, and phi constant and z constant, these are all plane surfaces. So these are the three surfaces. They intersect at the point P. These three plane surfaces, they intersect at the point P, and we have the coordinates for that, rho, phi and z. Now here, what are the limits of rho, phi and z? Rho can vary from 0 to infinity. Okay, rho can vary from 0 to infinity. Phi can vary from 0 to 2 pi. Phi, this angle, that can vary from 0 to 2 pi. Then it completes one rotation. Okay, can vary from 0 to 2 pi. And this rho can vary from 0 to infinity. And what about z? set can be positive or negative. Okay, positive or negative. This can be positive or negative, and it varies from minus infinity to plus infinity. Okay, that varies from minus infinity to plus infinity. Okay, so we have the this is how the rho, phi and z are varying. Then the transformation relation, how the x, y, z are connected to rho, phi, z. We know from here we can clearly see the x is, since this angle is phi, x is rho cos phi, and y is rho sin phi, and z is z itself. So these are the transformation relation, x equal to rho cos phi, y equal to rho sin phi, and z equal to z. So these are the transformation relations connecting the Cartesian coordinates and the cylindrical coordinates. Okay, so that we saw. So we have x equal to rho cos phi, y equal to rho sin phi. So if you take x square plus y square, that will be equal to rho square, and rho is x square plus y square to the power half, it's a constant. And if you divide y by x, we have the tan phi, and phi is tan inverse y by x. Okay, that we know. Then x, since x is rho cos phi and y rho sin phi, x is a function of rho and phi, and y is a function of rho and phi. Z is z. Okay, so we can write dx as dou x dou rho d rho plus dou x dou phi d phi. Since x is a function of rho phi, we can write like this. And what is dou x dou rho? That will be cos phi. And what is dou x dou phi? That will be minus rho sin phi. Okay, so we substitute that, and we have the dx as equal to cos phi d rho minus rho sin phi d phi. Same way, y is a function of rho and phi, so dy is this. This is dou y, dou rho, d rho, dou y, dou phi, d phi, and we find dou y, dou rho, and dou y, dou phi from this. Okay, so we have the relation dy is equal to sin phi d rho plus rho cos phi d phi dz, and ds square, that is given by dx square plus dy square plus dz square. So we substitute for dx is this, we substitute, and dy is this, we substitute. Okay, and dz is dz itself. Okay, so we substitute for dx, dy and dz, and you expand it, and certain terms get cancelled. Okay, certain terms get cancelled. Sorry, these two terms will cancel, and this will combine, this also will combine, this set will combine, this set will combine, and we have this relation ds square equal to d rho square plus rho square d phi square plus dz square, and ds square is equal to d rho square plus rho square d phi square plus dz square. So comparing with this general expression, okay, we have the general expression for ds square, that we compare with it, and comparing we get the scale factors as h1 equal to 1, h2 equal to rho, and h3 equal to 1. Also qi, the unit vector, this is the general expression for finding the unit vectors. Okay, rho, phi and z, we have to find rho, we have to find phi unit vectors. So we use this general expression, and R is this xi plus yj plus zk. So qi or q1, that is rho, unit vector rho, that is dou r dou rho, that is dou x dou rho I, dou y dou rho j, dou z dou rho k. Okay, and this is clearly 0 because z is z itself. So this is 0. Dou x dou rho we know, dou y dou rho we know, and we substitute and we get this. So this is the unit vector rho. Then unit vector phi, 1 by rho, because here this is the general expression for H2. We substitute this rho, and we have dou x, dou phi I, dou y, dou phi j. Substitute for this, and we have this. Substitute for this, we have this. And we get minus sin phi I plus cos phi j. So unit vector phi, that is minus sin phi I plus cos phi j. And unit vector z, that is dou r dou z, that is equal to k. So we have found the three unit vectors rho, phi and z by using the general expression. Then rho dot phi, we can show that rho dot phi is 0. Okay, this is rho and this is phi. So what will be rho dot phi? Dot product we are taking. Yes, yeah, we are taking the dot product. What will be it? Here we have cos phi I minus sin phi. So we will be getting minus cos phi sin phi. Here we have sin phi and cos phi. So plus sin phi cos phi. This will get cancelled, and rho dot phi, that is equal to 0. Same way we can show that phi dot z 0, rho dot z 0. So rho dot phi, phi dot z, rho dot z, this is equal to 0. So the cylindrical coordinate system is orthogonal. Okay, the cylindrical coordinate system is orthogonal, and cylindrical coordinate system, that is a curvilinear coordinate system, that is an orthogonal one. Okay, and we might be asked to prove the cylindrical coordinate system is orthogonal. And you know the direction of rho, phi and z here. The rho will be unit vector rho, that will be in this direction. Sorry, rho is increasing in here, so in this direction. So sorry. So rho will be in this direction, and z will be here. Z is increasing, so z will be in this direction, unit vector z. Phi is increasing this, so phi will be in this direction. Okay. So we have the rho and phi, z. So we have proved this, rho dot phi, phi dot z, and rho dot z, that are all equal to 0. Then the general expression for gradient is this. Okay, gradient of a scalar function is this. So we just substitute for that, and we can find the gradient. And also the general expression for divergence is this. We all know what is H1, H2, H3. In this case, we substitute, and this is the general expression for the Laplacian. Okay, this is the general expression for Laplacian. So we can find the Laplacian by substituting, and here we have the curl del cross, del cross V. This is the expression. So Q1 is rho, Q2 is phi, Q3 is z, H1 is, H1 is 1, H2 is rho, H3 is 1. We substitute for that, and we have the del cross V. So this is the expression for del cross V. Del cross V is this 1 by rho, and del square phi is this. You can just substitute, and we get del square phi, and we get the del dot V, and this is the expression for del dot V, and this is the expression for the del psi. This is actually del psi, this dot is not there. The gradient, this is the gradient, and it is this expression. V, we know, vector V that can be written like this in cylindrical coordinate system, V rho rho, V phi phi, V z z. Okay, so we have this expression, and this is how we treat the circular cylindrical coordinate system, an example for the orthogonal curvilinear coordinate system.